We usually think the modern world began with electricity, from the light bulb to the telephone, from radio to television, from computers to the internet, and then to today's chips, algorithms, and artificial intelligence. In the history we know, machines became smaller, quieter, and increasingly invisible. Everything was sealed inside boxes, hidden inside circuit boards, servers, data centers, and invisible lines of code. But in the 19th century, history once offered another possibility. Humanity had just entered the industrial age. Railways crossed continents, steamships crossed oceans, and factory chimneys changed the skyline of cities. For the first time, machines made people believe that technology could truly reshape the world. It was also in this age that a British mathematician seemed to glimpse part of the future ahead of time. Long before electronic computers and the internet appeared, he tried to build calculating machines with gears, bringing computing power into the industrial age. His name was Charles Babbage. If this path had continued, the 19th century might have entered a mechanical information age much earlier. But unfortunately, in real history, this path did not succeed. Babbage's machines never became the information infrastructure of the 19th century, and they did not lead the Victorian era into an age of mechanical computing. But what if they had succeeded? What if the British government, railway companies, banks, the Navy, and factories of the 19th century had truly begun using mechanical computers? What if the information age had not begun with silicon chips, but with brass gears, punched cards, and steam power? This is exactly the world imagined in the novel The Difference Engine. In that world, the Victorian era does not remain trapped in coal smoke, top hats, and horse-drawn carriages. It continues to grow forward. Railways become information networks. Cities become mechanical brains. The empire uses computers to manage shipping routes, taxes, wars, and population. Machines do not hide away. Instead, they become larger, more complex, more elaborate, and more dangerous. And these are exactly the most familiar images people associate with steampunk. What truly makes steampunk fascinating is that it is not far removed from reality. It does not create a world out of nothing. Instead, it takes hold of possibilities that once truly existed in history. Babbage's mechanical computers, Verne's submarines and long voyages, Wells's time machine and anxieties about the future, the giant machines of world exhibitions, and the coal smoke, class divisions, speed, and ambition of industrial cities. Then it asks one question. If the gears of the 19th century had never stopped turning, what would the Earth we live on today look like? In this episode, we begin with that question. Starting from The Difference Engine, we enter a timeline that never happened. We will see how a true steampunk world might change transportation, cities, war, social structures, and even space exploration. We will also see how real-world steampunk developed from Verne and Wells all the way to Castle in the Sky, Steamboy, BioShock, and Arcane. Today, we tell a brief history of steampunk, a history that never happened, but feels as if it almost did. In real history, the 19th century did not enter the information age. It entered the age of railways, steam, factories, and empires. Trains connected cities, steamships connected continents, telegraphs allowed messages to cross oceans almost instantly. Factories, banks, insurance companies, navies, and colonial governments all began to depend on increasingly vast tables, ledgers, routes, tax rates, and statistical data. In fact, long before electronic computers appeared, the industrial world had already begun producing enormous amounts of information. It simply did not yet have computers to process that information. Calculation still mainly depended on people. In the 19th century, the word computer originally did not mean a machine, but a job. It referred to people who performed calculations. They calculated navigation tables, artillery trajectories, insurance rates, and astronomical data. This work was repetitive, tedious, and easy to get wrong, but it was extremely important. A single wrong number could send a ship off course. A single wrong table could affect engineering, trade, war, and finance. It was in this context that Charles Babbage appeared. Babbage was a British mathematician and inventor, and he was extremely sensitive to errors. According to one famous story, while examining mathematical tables, he became frustrated by the large number of mistakes caused by human calculation. Then he had an idea. If people make mistakes when calculating, why not let a machine do the calculating instead? Around 1822, Babbage proposed the idea of the difference engine. This was not an electronic computer. It had no chips, no screen, no keyboard. It was a purely mechanical calculating machine. It was made of gears, shafts, wheels, and metal parts, and its purpose was to automatically calculate mathematical tables, handing complex calculations that had once required repeated human labor over to mechanical structures. Mechanical calculation did not begin with Babbage. In the 17th century, Pascal and Leibniz had already designed mechanical calculators. But what made Babbage different was that he did not simply want a machine to help people calculate. He wanted a machine to automatically, continuously, and reliably generate complex mathematical tables. In other words, he pushed mechanical calculation from a tool toward an automated system. And this step was crucial. The Industrial Revolution had already allowed humanity to hand physical labor over to machines. What Babbage wanted to do was bring calculation into the Industrial Revolution as well, to put numbers into machines, to put tables into machines, to turn reason, order, and rules into concrete instructions that could be carried out by metal parts. If the steam engine changed human power, then the mechanical computer attempted to change human judgment and management. For this reason, even though Babbage's machine was never truly completed, it left behind a key entry point for later fantasies about a mechanical information age. In real history, the difference engine was never truly put into large-scale use. Babbage's plan was too complex, too expensive, and extremely difficult to manufacture. The British government once funded the project, but it never truly took off, and it certainly did not develop into a foundational technology that changed society. Later, Babbage proposed an even more ambitious machine, the analytical engine. Compared with the difference engine, the analytical engine was much closer to the prototype of a modern computer. It was not only meant to calculate fixed mathematical tables, it tried to become a more general-purpose calculating machine. It imagined structures similar to storage, operation, and input. It could also use punched cards to input instructions. This was extremely important because punched cards were already an existing technology of the industrial age. In the Jacquard loom, punched cards could control the loom to weave different patterns. Babbage brought this idea into the field of calculation. In other words, machines could do more than repeat actions. They could change their actions according to instructions. This was the beginning of programmability. And in this story, another name is also extremely important: Ada Lovelace. She was not the co-designer of the difference engine.
Her important contribution was connected to Babbage's later machine, the analytical engine. In the 1840s, she translated an article introducing the analytical engine and added extensive notes of her own. In those notes, she did not merely understand how the machine could calculate numbers. She went further and realized that if numbers could represent musical notes, images, or other symbols, then the machine would not be processing only mathematics. It might be processing information in a much broader sense. This was an extremely advanced idea. Ada saw a completely new language, the possibility that humans could give rules to machines and machines could process information according to those rules. This is why Babbage and Ada later became two of the most important real historical anchors in steampunk imagination. They do not represent only a specific machine. They represent a technological path that never fully opened. If mechanical computing had truly matured in the 19th century, would the world have moved in another direction?
What if history split at this point? Then the Victorian era would begin to change. The first thing to change would almost certainly be the machinery of the state. In the 19th century, the places that needed calculation the most were governments, armies, banks, railways, shipping, and insurance. These systems already depended on data. If mechanical computers had matured early, they would have become the first users. So, in this timeline that never happened, a new kind of institution might appear in London, the calculation hall. It would not be quiet like today's data centers. It would be more like a precision factory. The entire building would be filled with gears, drive shafts, punched cards, metal wheels, mechanical printers, and long tables that never stopped vibrating. Steam engines would provide power. Clerks would organize data. Engineers would maintain the machines, and operators would feed stacks of punched cards into calculating devices. The machines would print out navigation tables, tax tables, railway timetables, and insurance rates. There would be no screens, no mouse, no blue glow, only paper tape, gears, ink, brass, and steam. But the tasks being handled would already be very modern. Information management, risk prediction, traffic planning, and war optimization. It would turn a vast empire into a system that could be calculated, scheduled, and statistically managed. At this point, the steampunk world truly begins to take shape. It allows the 19th century to enter, in a different way, an information age made of gears, machines, pipes, and steam engines. But problems appear with it. When powerful computing capacity enters the state, the military, banks, and colonial systems ahead of time, it brings not only efficiency, but also stronger control. Class conflict, labor issues, colonial systems, urban poverty, and the pressure of ordinary people being managed by vast machine systems would all appear earlier and more clearly. And this is where punk appears. Steam represents the power, speed, and order of the industrial age. Punk represents those who refuse to be completely swallowed by the system. Mechanics, workers, inventors, smugglers, pilots, and lower-class city residents would all search for their own place in this world, resisting the increasingly precise social order behind the machines. As this point of divergence moves forward, the 19th century is no longer only the age of steam engines and railways. It becomes a mechanical age, filled with both hope and unease. This contradiction is also one of the earliest two sides of science fiction. One side believes technology will carry humanity farther, toward the deep sea, the sky, the center of the earth, and unknown worlds. The other worries that technology will turn back and transform society, amplifying class, war, and power. Verne represents the former. Wells represents the latter, and steampunk forms between these two forces. It is fascinated by machines, but also suspicious of them. It longs for the adventure of the industrial age, but it cannot avoid the cost of that age. In the next chapter, we begin with Verne and Wells
and see how steampunk grew from 19th century science fiction into its own mechanical empire.
If mechanical computing had truly matured in the mid-19th century, it would not have changed the world on its own. A computer by itself cannot create an era. What truly changes an era is when it connects with other technologies: railways, telegraphs, steamships, steel bridges, urban pipes, ocean routes, factory systems, banking networks, and colonial trade. All of these already existed in real history, but in this branching timeline, mechanical computing reorganizes them. And so the steampunk world enters its second stage, a mechanical empire supported by railways, telegraphs, steam power, and computing systems. The first thing to change would be the railway. In the 19th century, railways were already one of the most important infrastructures of industrial civilization. In real history, railway companies relied on timetables, telegraphs, and human dispatchers to maintain the system. But in a steampunk world, mechanical computers would join that system. Railway companies could feed stations, routes, cargo, passengers, coal consumption, and maintenance cycles into calculating machines. The machine would not simply produce a new timetable, it would help redistribute capacity across the entire railway network. Which line should have priority, which cargo should move first, which train should give way, and where more coal and maintenance crews were needed. Telegraphs would then send these dispatching results to different stations, perhaps even directly to the driver's cab. The information could be turned into punched cards by a special device, and the driver would insert those cards into the train's control system, allowing the train to run according to the latest instructions. In this way, railways would no longer be just a means of transport, they would become a logistics network supported by computation, communication, and steam power. Transport capacity would rise sharply, and the most visible cost would be denser white steam over the city. Cities would change along with it. In real history, London, Paris, New York, and Chicago were already expanding rapidly in the 19th century. People poured into cities, factories occupied riverbanks, railways cut through urban districts, coal smoke covered the sky. In the steampunk timeline, this expansion would become more organized and more intense as logistics systems became more efficient. City administrators would need to process more information: water supply, gas, sewers, police, hospitals, traffic, fires, disease, and food distribution. All of this data would be sent into urban calculation halls, then distributed by telegraph to different departments. The city would begin to be managed like a machine. As the management system became more precise, class divisions inside the city would also become more fixed. The upper level of the city would be clock towers, glass domes, banks, exchanges, government buildings, and the mansions of the powerful. The middle level would be elevated railways, telegraph lines, pneumatic tubes, and middle-class neighborhoods. The lower level would be boiler rooms, sewers, subway tunnels, workers' housing, coal depots, and slums. This kind of city would be spectacular, but also extremely heavy. It would contain modern wonders made of glass, brass, and steel, but also coal smoke, noise, poverty, and class division. This is one of the most important conflicts in steampunk aesthetics. On one side, the elegance of the industrial age. On the other, the cost of the industrial age. In the same city, aristocrats could sit in brightly lit airship restaurants overlooking the Thames. Bankers could wait in calculation halls,
for machines to print the next round of trade forecasts. But in the lower city, workers would still have to keep these machines running amid coal dust, noise, and heat. These imaginings did not come out of nowhere. The real 19th century was already an age in which machines were constantly changing the world. Railways shortened distance. Telegraphs accelerated information. Steamships connected oceans. Factories reshaped cities. For people at the time, the future was not a distant idea. It was something changing right in front of their eyes every day. It was in this atmosphere that 19th century science fiction writers began pushing real machines further forward. They imagined longer voyages, more powerful vehicles, and also the loss of control and fear that technology might bring. These works later became some of the most important sources of steampunk. The two most important figures here are Jules Verne and H.G. Wells. Verne was not writing steampunk in the sense we use the term today, but his works left steampunk with very important DNA. The Nautilus, in 20,000 Leagues Under the Seas, is the clearest example. It is a submarine, but also a moving mechanical palace. Captain Nemo uses it to leave the nations of the land behind and dive into the underwater world. In this setting, the machine is not a cold tool. The machine is a form of freedom. It can carry people across the ocean and into unknown territory. It allows someone to leave the old order and build his own kingdom. This is the most fascinating part of Verne's imagination. From this perspective, 20,000 Leagues Under the Seas is almost an early spiritual model for steampunk. Not because it has brass and gears, but because it believes that a powerful enough machine can carry a person to the edge of the world. But 19th century science fiction was not only optimistic. On the other side was H.G. Wells. If Verne wrote machines as vehicles toward distant places, Wells was more concerned with another question. Where would technology take society? On the surface, The Time Machine is a story about time travel. But what truly makes it frightening is not only its future world, but the class division inside that future world. In Wells's imagination, human society eventually splits into two groups. The Eloi on the surface seem light, fragile, and carefree. The Morlocks underground labor in darkness and return to the surface at night. This setting feels very steampunk. As mentioned earlier, a steampunk city itself often has two layers. Above is the respectable world. Below are the people who keep the machines running. Wells shows us that the future of industrial civilization is not necessarily progress shared by everyone. It may also push class division into a more extreme form. By the time of the War of the Worlds, this unease takes another form. The British Empire was used to looking down on the world through its technological advantage. But in the War of the Worlds, Britain itself becomes the invaded side. The Martians' tripods, heat rays, and biological weapons turn London into a conquered city. This is important for steampunk because it reminds us that industrial age imagination is not only about progress and adventure, it also contains a reverse fear. When humans believe machines can conquer the world, they will inevitably imagine a machine stronger than themselves. Verne and Wells can be seen as two sources of steampunk. Verne's mechanical adventures gave steampunk long voyages, exploration, and romantic imagination. Wells's technological anxiety made steampunk more than just beautiful machines. It also gave it the shadow of class, war, and loss of control. Later, the distant worlds imagined in Verne's spirit were indeed opened again and again by machines. The deep sea, the sky, the polar regions, and continents were gradually connected by industrial-age vehicles. But Wells's anxiety also arrived. It did not come from Mars. It came from humanity itself. After entering the 20th century, the machines of the industrial age were systematically brought onto the battlefield. Eventually, industrial civilization turned into a giant war machine. This sentence has two meanings. First, entire nations were drawn into war production, and society itself became a machine built to serve war. Second, war also created more and more literal mechanical giants. Giant cannons, giant airships, giant war vehicles, armored trains, and mobile fortresses. For example, during the First World War, Zeppelin airships were used for reconnaissance and bombing. They were huge and slow, but they could cross battle lines and cast the shadow of war over cities. During the Second World War, Germany built the Gustav railway gun. It was an extremely large railway cannon that required special tracks, large numbers of personnel, and heavy equipment just to deploy. The Soviet Union also experimented with many exaggerated armored concepts, such as giant wheeled tanks, land battleships, and enormous aircraft capable of carrying smaller planes. These examples show one thing. People in the industrial age truly believed that bigger itself could mean power. Steampunk takes this impulse and pushes it even further. In steampunk warfare, weapons are not built for lightness. They are built for weight, pressure, armor, noise, and continuous operation. This kind of imagination appears often in steampunk works. The Goliath battleship in Castle in the Sky is a typical steampunk-style aerial giant. It is both an aircraft and a flying fortress. The giant mechanical spider in Wild Wild West pushes the idea of the war machine directly into the realm of an exaggerated mechanical monster. Mortal Engines goes even further, turning entire cities into giant machines that can move, devour, and fight. In BioShock Infinite, the floating city of Columbia is not strictly traditional steampunk, but it follows the same idea, turning an entire city into a massive platform of technology, power, and military force. In other words, one of the most fascinating parts of steampunk is that it constantly pushes industrial age machinery to its extreme.
But steampunk is not only about making machines bigger. It also translates modern technology into the technical language of the 19th century. It rewrites problems that, in the real world, were solved by oil, electricity, and electronic systems, and imagines them being solved instead by gears, steam, pressure, and mechanical computing. For example, cars would not use internal combustion engines and gasoline. They might use steam power, pure electricity, or even hybrid systems based on compressed air and mechanical transmission. Aircraft could be replaced by airships, ornithopters, aerial docks, and steam-electric hybrid flying machines. Computers would not become silicon chips. They would continue along the path of the difference engine and the analytical engine, developing into gear-driven calculation halls, punched card terminals, or even extremely miniaturized mechanical calculating devices. But the problem is that not every modern technology can be solved this way. So, steampunk works often use a more direct solution. They give the world a core technology that goes beyond reality. The levitation stone in Castle in the Sky is one such example. It solves the problem of how giant cities and ancient machines can rise into the sky. The steam ball in Steam Boy works in a similar way. It compresses steam into an almost miraculous energy source, allowing steam not only to drive trains and factories, but also to support city-scale mechanical spectacles. The powerful magnetic coils in Wild Wild West translate the modern military idea of precision guidance into a 19th century-style mechanical device.
They use exaggerated electromagnetic equipment to simulate the effect of target tracking and guided weapons. This setting certainly does not hold up under close examination, but it fits the logic of steampunk very well. Simply put, steampunk lets 19th century machines perform the tasks of modern technology. From another angle, this is also its boundary. Modern technology cannot simply be copied directly into the world. It must be translated into the technical language of the steam age.
If oil, internal combustion engines, airplanes, tanks, and modern military-industrial systems are introduced directly, then it begins to turn into diesel punk. Examples include Metropolis, Sky Captain and the World of Tomorrow, and Iron Sky. If the focus shifts to Eastern materials, mechanical devices, and classical warfare imagination, it may become silk punk. If it shifts to networks, cybernetic bodies, artificial intelligence, and giant corporations, it enters cyberpunk. If it shifts to civilizational collapse, resource struggles, and wasteland vehicle modification, it moves closer to wasteland punk. Generally speaking, the era that fits steampunk best is from the mid to late 19th century to around the First World War. After that, steam engines were gradually replaced by internal combustion engines, electric motors, and the oil-based system, and the world began to move on to a different technological path. But the question is, must steampunk remain in the Victorian era? If the gears of the 19th century had never stopped turning, could they continue into the Cold War or even all the way to the moon?
If we continue moving along this timeline, and gears, boilers, mechanical computing, airships, and brass industrial systems never leave history, then can steampunk describe later eras, the Cold War, for example, the space race, or even a steampunk version of a moon base? Physically speaking, relying only on a traditional steam engine could never send anything directly out of the atmosphere. Steam engines are too heavy, require water and fuel, and do not have the energy density needed for space launch. But, as mentioned in the previous chapter, steampunk does not mean everything must literally be powered by steam engines. It is more about using gears, boilers, brass, and mechanical structures to reimagine modern technology. The Cold War in this world would not necessarily be made of white rockets, plastic instrument panels, and electronic screens. It would feel more like a gigantic project built from railways, military factories, calculation halls, launch towers, and state propaganda. In real history, the space race was a contest in which the United States and the Soviet Union compressed military industry, computation, materials, fuel, communication, and political messaging into one goal. Who could put a satellite into orbit first? Who could enter space first? And who could put a human on the moon first? In the steampunk timeline, that logic would not disappear. National competition would still exist. Military-industrial systems would still exist. The need for calculation would still exist. Space would still be seen as a strategic high ground. Only its appearance and technological path would be rewritten. Likewise, a steampunk moon base would not look like a modern space laboratory. It would look more like a mining colony transported onto the lunar surface. Glass-domed greenhouses, riveted steel corridors, brass valves, enormous pressure gauges, mechanical air circulation systems, lunar railcars, spacesuits resembling deep-sea diving suits, and a mechanical calculation hall responsible for orbital calculations, oxygen distribution, and resource management. The same logic could also be used to imagine a steampunk version of the nuclear age. So steampunk does not have to remain limited to gas lamps and London streets. As long as its rules are clear enough, it can describe the Cold War, space, moon bases, and even larger worlds. But the appearance is not everything. Steampunk cannot have only steam. It also needs punk. At this point, we can re-examine works such as Castle in the Sky, BioShock Infinite, and Mortal Engines.
Laputa, in Castle in the Sky, is an ancient super-technological ruin in the sky. It looks like a fairy tale, but behind it are military power and the desire to rule. Columbia, in BioShock Infinite, is a city floating in the sky. It has a spectacular retro-futurist appearance, but inside it are nationalism, class oppression, and political violence. The moving cities in Mortal Engines turn the city itself into a predatory machine. Cities are no longer fixed to the land. They directly devour other cities. What these works truly care about is not where technology takes the city, but whether the deeper problems change after the outward appearance has changed. So if steampunk enters space, the most interesting question is not what the moon base looks like, it is whether humanity brings the same problems to the moon. Who owns the launch tower? Who controls the oxygen? Who manages the orbit? Who decides who owns the lunar minerals? Who gets to live inside the glass domes? Who has to work in the underground mines? When these questions appear, the punk in steampunk truly appears. On the moon, the rebels would no longer be mechanics from the lower levels of London. They might be maintenance workers in oxygen factories, lunar train drivers, orbital calculators, doctors in mining districts, or mechanical programmers secretly altering paper tape programs. The system they face would no longer be only an imperial city, it would be a vast mechanical order connecting Earth, orbit, and the moon. At this point, steampunk has been pushed to its limit. In the next chapter, we return to reality and look at how this word, invented in 1987, became a global fantasy.
The real world did not follow that steampunk timeline. The real 20th century went down another path. Electricity replaced gas lamps. Internal combustion engines replaced steam engines. Cars and airplanes changed transportation. Plastics, aluminum alloys, vacuum tubes, transistors, chips, and the internet gradually became the foundation of the modern world. Machines became more powerful, but they also became smaller, more sealed, and more invisible. By the second half of the 20th century, it had become difficult to understand how a machine worked just by looking at it from the outside. There are no turning gears inside a phone. There are no swinging connecting rods inside a computer. Technology became more efficient, but also more abstract. And it was in this context that people began looking back and imagining the road that had never happened. What if modern machines had not become so thin, quiet, and impossible to take apart? What if they were still visible, tangible, and repairable? What if the future were not made of chips and plastic, but of brass, steel, glass, and gears? What would the world look like? This is why steampunk reappeared in the late 20th century. It is not a genre truly left behind by the 19th century. It is a later reimagining of the 19th century created by people standing inside the modern world. In 1987, American writer K.W. Jeter used the word steampunk in a letter to Locus magazine. At first, the word carried a bit of a joke. Cyberpunk had already become a striking term in science fiction at the time. Cyberpunk was concerned with computers, networks, giant corporations, hackers, cybernetic bodies, and lowlife inside a high-tech society. Jeter's steampunk was almost saying if cyberpunk belongs to chips and networks, then another kind of science fiction can belong to steam, gears, and the Victorian age. The word was later used to describe a group of works with Victorian fantasy, mechanical technology, and an alternate history atmosphere. One of the most important among them was the Difference Engine, published in 1990 by William Gibson and Bruce Sterling. The Difference Engine was not the first work with a steampunk feeling, but it almost perfectly clarified steampunk's most important historical question. If Babbage's mechanical computer had succeeded, if the information age had arrived early in Victorian Britain, and if computing, politics, finance, policing, media, and imperial management had all been transformed by mechanical systems, what would the modern world have become?
From this point on, steampunk gradually developed several stable features. First, it usually returns to the 19th century, especially the Victorian age and the world after the Industrial Revolution. This is a world of gas lamps, railways, steamships, factories, iron bridges, London streets, imperial order and class divisions. Second, it adds advanced technology, mechanical computers, giant airships, automata, mechanical prosthetics, steam weapons, floating cities, underground machines, and strange inventions. These technologies do not seem to belong to the real 19th century, but they feel as if they naturally grew out of it. Third, it emphasizes visible mechanical structure. Steampunk machines are usually not completely sealed. They expose gears, valves, pipes, pressure gauges, pistons, rivets, and drive shafts. They make the audience feel as if they can understand how the machine works. Fourth, steampunk often contains social conflict. Aristocrats and workers, empires and colonies, capitalists and mechanics, the military and inventors, the upper city and the underground poor. Steampunk is both nostalgic and anti-nostalgic. It misses visible machines. It misses an age when machines could still be taken apart and repaired. But it also understands that this age contained class oppression, colonial expansion, and industrial exploitation. It does not truly treat the 19th century as a perfect era. Instead, it rewrites the 19th century, preserving its mechanical romance, amplifying its technological imagination, and bringing out its contradictions and problems at the same time. Later, steampunk gradually moved from literature into film, animation, games, music, fashion, and community culture. But no matter how its form changes, the core questions of steampunk remain the same. When technology becomes more and more complex, can humans still understand it? When systems become larger and larger, can humans still change them? When machines become more and more powerful, can humans still keep their place? This is why steampunk has remained popular from 1987 all the way to today.
If the gears of the 19th century had never stopped turning, what would the world have become? The answer may not be what matters. What matters is whether, when we look into that parallel world of brass and steam, we can still see ourselves.
This is BHE, Brief History of Everything.